Hi everyone, I'm Pranav Choudhary and welcome to Vedantu Olympiad School. Today we will be doing inversion. So there was one class on inversion before, and in that class, Abhay sir basically discussed the basics of inversion and like how things work, and he discussed a couple of problems, if I'm not wrong. In today's class, we will be reviewing the basics. Like I'll be telling how things work. I'll be doing that quickly, and if you want to see it in like a detailed manner, you can see that video. I'll be doing it in like 10-15 minutes so that you don't, if you have not seen the video, you can still continue with this one. And then we'll be discussing different types of inversion. For example, orthocenter inversion, in-circle inversion, and then there is root BC inversion and root BC by 2 inversion. So when we discuss different types of inversion, you will realize how stuff actually works in inversion, which is really nice. So let's get started. So first of all, what is inversion? Inversion is a function which sends one point in plane to another point in plane. How does it send? So basically, suppose you have this circle. Let's call this circle gamma, and you have this center of the circle O. Suppose you have this arbitrary point P lying anywhere in the plane. I'm taking it inside the circle right now. You join this line OP and draw the point P star. Okay, let's say P dash, it's easier to write dash. P dash, which lies on the line OP, such that OP into OP dash equal to R square, where R is the radius of the circle. So this distance is R. And let's say this point is somewhat like, it will lie here, P dash. So we say that P dash is inverse of P with respect to gamma. This part is important. Like inversion is always defined with respect to a circle. You cannot just say that this point is inverse of this. Like if you're doing a problem and if you have discussing a particular inversion in that problem, then it makes sense to say that this thing is inverse of that. But in general, you just cannot randomly say that this should be inverse of that. You should take care about that. But what's the circle about which you're inverting? Now, how do things work under inversion? So if we have this point, okay, let's first consider a circle. And let's consider a point inside the circle. Where do you expect P dash to actually lie? Note that OP into OP dash should be R square. Since OP is less than R, because P lies inside the circle, right? And this distance should be R. So this is less than R. So we get OP dash should be greater than R. It means P dash lies outside the circle. Similarly, you can show if P lies outside, then P dash lies inside. Moreover, if there is a point, let's say A lying on the circle itself, what will the inverse of A be? Then notice that OA is R, and we need OA into OA dash equal to R square. This means OA dash should also be R, and this should lie on the line OA. Basically, it's ray OA to be precise. So the inverse of A is just A. Inverse of A will be A. Okay, I hope this part is clear. Moreover, it's easy to see that the inverse of O should be in the point at infinity. How can we think about this is OO into OO dash should be R square. Now OO dash is basically R square by OO, which is just R square by 0 in some sense, which is infinite. Okay. Here's a nice property. If P dash is inverse of P, this implies P is inverse of P dash. This is like very easy to prove using the definition of inversion. So basically, OP into OP dash is R squared, right? And the order will be something like, let's assume here is point O, here is point P, and there would be some point P dash here, right? Now we have that P dash is inverse of P, so this thing is true, where R is the radius of the circle of inversion. And now how do we show that P is inverse of P dash? This just follows, right? You can just write OP dash into, let's say the inverse of P dash is something P double dash. This should be R square. But we know R square is also equal to OP into OP dash. So we just get OP double dash equal to OP. And since it lies on ray OP dash, there is only exactly one such point. So P dash is equivalent to P, and hence we are done. This is a very nice property. It tells us that if something, okay, I'll tell what it tells later when we see how lines and circles work in the inversion. Let's talk about a line now. Suppose I have this circle of inversion with me. I consider a line passing through the circle, passing through the center of the circle. Let's call this L. What will the inverse of L be? Also, in the session, I'll be denoting inversion function by phi. It's just an easier way to denote. So when I say phi of x, it means the image of x under the inversion which we are talking about. I'll mention what phi is. And when I say suppose phi of L, it means the image of line L under the inversion which we are talking about. So what will phi of L be here? Consider any random point lying on this line, let's say P. Notice that P, phi of P, will be some point lying on OP. And OP is just the line L. So image of any point P under the inversion will be another point lying on this line. Right? So it means phi of L is equal to L. Okay, but notice one thing. We say that this line L goes to itself. This does not mean that if we take any point P, it should also go to itself. P will go to some point inside it, right? It will go to P dash. Yeah, so I hope that is clear. How does a line work? Let's consider a line not passing through the center. Suppose this is L here. We have to talk about how the inverse of this thing will look like. What we do is we draw a perpendicular to this line and call this point, let's say A, and the inverse of this point is A dash. We pick any random point X lying on L and we want to see how phi of X looks like. Phi is the inversion around the circle gamma, about the circle gamma. So consider X, consider this line OX. X dash should lie somewhere here, right? Can you notice a nice property? Like how do you characterize X dash? By definition of inversion, OA dash into OA equal to R square, where R is the radius, right? And since X dash is also the inverse of X, OX dash into OX should also be R square, right? So this means these two things are equal. OA into OA dash equal to OX into OX dash. Do you see like power of point coming here? So XX dash and AA dash meet at point O, and we have that OA dash equal to OA and OX dash equal to OX. So AA dash X dash x is cyclic, which means this angle was 90 degree. So this will also be 90 degree. Also, for those of you who don't know what power of point is, you don't need to know it. You can just do it by similarity. So this thing is equivalent to OA by OA by OX dash equal to OX by OA dash, and this angle is equivalent. So this gives us triangle OAX similar to triangle OX dash H, and similar triangles. So this is just given as angle OAX equal to angle OX dash H. So we get that any point lying on this line, the inverse of it is a point x dash, such that angle OX dash A dash is 90 degree. So if we draw the circle with diameter OA dash, every point should lie on here, on this, right? Because if we consider this point y, then, and if you consider this point y dash, then this angle is also 90 degree because OA dash is the diameter. So we see that if you consider a line, then phi of line which does not pass through center is a circle passing through the center of the circle of inversion. I hope that's clear. Also, in the proof of this, we notice a nice thing. So if this is a circle and we consider 2 points, let's say A and B, we consider their inverses A dash and B dash. Then can you see that A, B, B dash, A dash and A, these 4 points are concyclic. I just proved it in the proof of that thing, right? By power of point it follows. And if not power of point, then you can just see by similarity, these two angles will be equal. So this is a cyclic quadratic. Now, how I like to think about this is, suppose I give you some random circle. I give you one point A, not lying on the circle. Notice that. And the inverse of A under this inversion. Under the inversion about this circle, comma. Let's call this A dash. I give you any other random point B. Can you construct B dash using only a compass and a straight edge? Think about this for 1 or 2 minutes. It's easy after you get hold of this thing, this cyclicity. If you cannot get it directly, I would recommend you pause the video and try to prove it yourself. It's a nice thing. Okay, I'll go with the proof. Consider the circle A, B, A dash. Join the segment OB and consider this intersection B dash. This will be the inverse of B under gamma. Why is this true? Because by a previous lemma, if B dash is inverse of B, then B should be inverse of B dash. And if you consider AB dash, these two are inverses, right? So these 4 points should be concyclic. That is why this is true. I hope you get this. The last thing we talk about in this is, how do circles work under inversion? So suppose this is my circle of inversion. I consider, okay, let's call this gamma. I consider a circle which passes through the center of the gamma. Let's call this omega. what will phi of omega be? Okay, we talked in like a few minutes ago that if phi of x is x dash, then phi of x dash is x, right? So if x dash is inverse of x, then x is inverse of x dash. This is what we said. So we know that the inverse of a line which is not passing through O will have its inverse as a circle which passes through O, right? So let's say that this line has its inverse as gamma. So we have that phi of L is gamma. Consider some random point x on L. Its inverse will be x dash lying here, right? Phi of x is x dash. Okay, I have used x already, so let's just call this t. Phi of t is t dash. This means phi of t dash should be t. So any point lying on gamma will go to this line L, will go to a point lying on this line. So can I say phi of omega will just be L, right? So basically, the nice thing which I had to set there was, if any object goes to another object under inversion, then that second object also goes to the first object under inversion. I mean, this sounds in a confusing way, but you can see from this, if phi of L is omega, then phi of omega is L. I hope this is clear. Yeah. Okay, so we have talked about the circle which passes through a center. How about we consider a circle which does not pass through center? Okay, so this is circle gamma, this is circle omega. Also, this pink line is drawn such that this is the diameter of omega. So like AB is diameter of omega. This is how I draw this. We can construct the inverses of A and B. So here will be somewhere B dash and here will be A dash. Okay, let's consider a point X lying on the circle and its inverse. Let's say this X and this is some X dash. We have that angle AXB is 90 degrees, right? AXB is 90. Okay. Now notice that angle B dash X A dash is equal to angle OX dash A dash minus angle OX dash B dash, right? So this angle is this big angle minus this small angle, right? Now angle OX dash A dash, this angle. Notice that X A X dash X dash A dash X A are cyclic because X dash and A dash are inverses of X and A. And by that lemma which I'm saying since starting, these 4 points should be concyclic. I hope you are used to that lemma now. So angle OX dash A dash, this should be equal to angle OAX. And angle OX dash B dash similarly should be angle OBX. Now notice that angle OAX will be 180 minus angle XAB. This thing minus angle OBX, which is just angle AXB, and this thing is just 90. Right? So we get that this angle is also 90 degrees. So if we consider the circle with diameter a dash b dash, the figure is horrible. Just bear with the figure. This is the circle with diameter a dash b dash, unfortunately. Yeah. So if you consider the circle with diameter a dash b dash, x dash should lie on that circle. So we get that image of this smaller circle omega. Omega dash is also a circle, right? Now, what about like if I say, is it possible that if omega is a circle, then phi of omega, where phi is a inversion and about some random circle, is equal to omega. So let's think about what the condition is saying us. If you have this random circle, this is gamma about which we'll consider our inversion, and this is omega. This is the center. Let's consider a random chord xy of omega passing through O. Notice that this says that phi of x, since omega goes to itself, x should also go to a point lying on omega. So x can either go to x or y, right? Because x will go on a point lying on this OX and lying on omega. So there are only two such points, x or y. Clearly, phi of x cannot be x, because that is only true when x lies on this gamma. So this means phi of x should be y. This means OX into OY should be R square. All right. What if I consider this intersection point? Let's call this A. This means OA into OA. But this does not work that this way, no? Yep. I just want to do this. 1 minute. Let me think about this. Oh, yeah, I got it. Yeah. So notice that R square is also equal to OA square. This is what I meant to say. Yeah. This is OA. This is the radius basically, right? So now, since OA square is equal to OX into OY, do you see that OA is tangent to omega, right? So basically, this is tangent. So if you consider the center of this circle, let's call that O dash, then this should be 90 degrees. And this is just the angle between the two circles, right? Because these are tangent to the circle at that point. So these are orthogonal circles. So we get that if omega is a circle orthogonal to gamma, then phi of omega under gamma is omega. This is a nice property which is used in quite a few problems. In fact, I did a problem inversion today and it was used in that problem itself. It was amazing. I might share that problem in another class of inversion where we'll just discuss the problems. Also, yeah, okay, there is one more thing to cover in the basics, which is the distance formula. So if I have 2 points A and B, I'm given that AB, I'm given the length of AB. I need to find A dash B dash. How do I find? Okay, the proof is by similarity. It follows from the same ideas we discussed before. I'll just state the answer and the proof is left as an exercise to you guys. You can pause the video and try to prove it. A dash B dash is equal to AB into R square divided by OA into OB. Yep. This is used in some problems. Like I don't really like this formula because it's like very length-washy, but yeah, it is used rarely, but somewhere. Also, here is a nice thing to note about angles, which this thing should be, like instinct. What do you say? Intuitive enough. So if I'm given this angle OAB, after inversion, you can see that angle OAB is equal to OB dash A dash. This should be intuitive, that if I am given angle OAB and I am inverting, O is the center of inversion. Notice that. This thing should be angle OB dash A dash. This should be very intuitive to you. You should not need a diagram to this. This should be like, memorized in some sort. That, okay, OAB, so this gets switched and there comes a dash. But you should know the proof in mind and how things are working out. Not just memorize, but yeah, intuitive. Okay, I repeated it too many times. That's not good. Okay. So this was the introduction part. I guess it was a bit quick, so you can watch it again if you need, or else we can just move on to the problems and you can see how things are going around the problems. Okay, let me import the first problem. Okay, I'll just put it. So the question is, also in this class I'll be doing on Miro only. I don't want to use GGB because we should be used to freehand diagrams or pencil and scale diagrams. We should not be using GGB ethically. Yeah. So the problem states you have this circle. AB is the diameter in the circle. And D and C are some random points lying on the circle. You define the point as AB intersection CD. This is point M. This is the center of the circle O, which is midpoint of AB basically. You draw the circles OAD. And OCB. They intersect at point K. You need to prove angle OKM is 90 degrees. This is what we need to prove. Think about this problem for 4 or 5 minutes. And if you need more, you should take more time. And then when you have given up, you should see the solution. Okay, I'll give you 5 minutes so that you can pause the video and try out the solution. Okay. So we discussed the motivation and stuff. How do we approach this problem? Okay. Notice that we have 3 circles in this problem. The circles are ABCD, OCB, and OAD. There are so many circles to deal with. And notice that O is a nice point. It is the center of ABCD and 2 circles pass through O. So if I invert about O, I know that these 2 circles will go to some line. I don't know what line right now. Okay, so it seems very intuitive to invert about O. And if I'm inverting about O, I also want to take care of the circle ABCD. What if I take my radius to be OA? In that case, A goes to A, B goes to B, C goes to C, D goes to D. Because the circle O comma OA is just the circle ABCD, right? Basic circle with center O and radius O. So what I'm doing is I'm defining my function inversion phi about the circle ABCD. Okay. So how do the points look? Now this AOD, circle AOD, should go to a line. Okay. So A and D lie on this orange circle. So A goes to A, D goes to D, right? And this circle goes to a line. We know 2 points lying on that line. Can we just draw the line? Here. This is the line. So this means phi of circle OAD is just the line AD. Similarly, you can get that phi of circle OBC is BC. Oh, also I forgot to say this thing before, but intersections are preserved in inversion. This is not very hard to show, and it's, yeah, you don't even need to show this. It's like easy to see itself. You can try to prove it if you need to. But yeah, intersections are preserved. So now K is OAD intersection OBC, which means K dash should be, what's the inverse of OAD? AD. What's the inverse of OBC? BC. So we get that this point is just K dash. Now let's talk about M. Since M lies on AB, the inverse of AB is just AB because this line passes through O. So M lies on somewhere on AB, like M dash lies on AB. And M lies on CD, right? So it's a line. So the inverse of this is a circle passing through O. And since this line has C and D has 2 points, which goes to itself. So the inverse of this line should be the circle OCD. This point should be M. Okay. This doesn't. Okay, just bear with the circle, however it looks. This is what happens in freehand, and you should get used to it. Right. This is M dash. Now we need the original question asks us to prove angle OKM is 90 degree. This is equivalent to proving angle OM dash K dash 90. I said you to keep this thing very intuitive, right? And it helped us. So we need to prove this angle is 90. How are we going to do this? Notice this black circle. I'll change the color of the circle to something else. Nice color. Okay. Notice this sky blue colored circle. This passes through O. Okay. And its space. I erase this stuff. Yeah. Okay. Now yeah. So this sky blue circle we are talking about, it passes through O. What is O? Midpoint of AB. It also passes through D. Notice that AB is diameter. So this angle is 90. So it passes through the feet of altitudes in triangle K dash AB. So this circle, sky blue circle, is basically 9-point circle of triangle KAB, which is nice. Why? Because M dash is a point lying on AB and on the 9-point circle. We already know that O is the midpoint, so M dash cannot be the midpoint. M dash should be the feet of altitude, right? Because like if 9-point circle passes through midpoints and the feet of altitude. So we get that M dash is the feet of altitude on AB in triangle K dash AB. O dash. So this just gives us angle AM dash K dash is 90 degree, which is just equal to angle O K dash M dash. So we are done. I'll go over the motivation once more. We have two circles passing through O. This one, this one, and this one. When we invert about O, these two circles go to a line. We pick the radius OA because then ABCD goes to itself, which is a nice circle. Moreover, OAD goes to AD, OBC goes to BC. Everything is nice. What we want to prove, angle OKM is 90 degree. Under inversion, we need to prove OM dash K dash is 90 degree, which is also nice thing. It's not a complicated angle. That's why we did this inversion. When you usually do inversion, what happens is you think about some inversion. This is what I do. I will just quickly consider all the lines and circles which I'll get after inversion. If they look nice enough to me, I'll invert. If they look that this circle is very random or you don't know how to define the circle, I usually don't invert. This thing works like 90% of the times. Rest 10% questions are like very, what do you say? Ajib kind of types. I cannot recall the word. So yeah, I hope you get my point. Okay, now let's move on to some nice kinds of inversion. So let me change back to pencil. First, we'll do circumcircle inversion. What this inversion does is, if you have some triangle ABC, with circumcenter O, we perform an inversion with center O and radius OA, which is just inversion around the circumcircle. How is this nice? A goes to itself, B goes to itself, because all of these are points lying on the circle of inversion, and C goes to itself. So circle ABC goes to itself, and everything just moves around this thing. So it's nice enough when you have a circumcircle. To like support my point, I'll give one example problem. Let me find the problem. Okay. So this is the problem. In triangle OBC, in triangle ABC, let O be the circumcenter. Suppose circle OBC intersects AB and AC at B1 comma C1. Circle OCA intersects BC comma CA or BC comma BA, sorry, at C2 and A2, and circle OAB intersects CA and CB at A3 comma B3. Then prove that A1 A2, oh no, A1 doesn't exist, A2 A3, B1 B3 and C1 C2 are concurrent. Okay, actually, if you are versed enough with inversion, you don't even need a diagram for this. You can just work out the things in your mind and by visualizing which stuff goes to where. But right now I'll use GeoGebra for this problem because the diagram, freehand diagram will be very messy and I don't want to confuse anyone. So I'll just use GeoGebra. But in practice, you guys shouldn't use it. We are given the circles OBC, OCA, and OAB. I'll consider them in different colors. Okay. Oops. This point is B1 and okay, the things are not really okay, this looks better. This point is A2 and this point is C2. This is C1. Okay. This is A1. And this is, oh, this is A3. Ah, the numbers are confusing. And this is B3. This is the data. We need to show that B1, B3, C1, C2, and okay, amazing. A2, A3 are concurrent. So this basically spoils the problem. You can see that all these three lines are concurrent at O. And now also I was talking about circumcircle inversion. So you guys know that we have to invert about circumcircle. So let's do that and see how things work. I'll insert this. Okay, so under inversion, notice that what's the image of OBC under circumcircle inversion? Since it's a circle passing through center, it should be a line. It has B and C lying on it, which go to themselves. So OBC goes to BC. This thing goes to BC. Which means B1 goes to OB1 intersection BC. Right? Or this will go to this only, right? Yeah, this makes sense. And C2 goes to OC2. One second. Yep. This should be C1. OC1 intersection C2, intersection BC. Okay. Now, if we consider the circle OAC, this should go to AC, which means C2 goes to OC2 cap AC. And A2 goes to OA2 cap AC. Now the thing is, from these two things, you should get a feel that C1 and C2 are linked and they should be collinear with O. But this doesn't really prove. This is like, looks very messy, right? Here is a better way to do this. How is C2 defined? C2 is OAC cap BC, right? What did I say? Intersections are preserved under inversion. OAC goes to AC, BC goes to OBC. What is this thing actually? This is just C1, right? Which means C2 goes to C1 under inversion. And what do we know? If X goes to X dash under inversion, then O, X and X dash should be collinear, which means O, C1 and C2 are collinear, which means these 3 points are collinear. Similarly, we will get O, A3, A2 are collinear and O, B1, B3 are collinear. This is very nice. So we proved the problem basically, right? One more thing to notice in circumcircle inversion, which we just did in this problem, is if you consider the circle OBC, this goes to BC. And now we have even seen how is this thing useful, right? So this was all about circumcircle inversion. I hope that was clear. Okay, so the second type of inversion is in circle inversion. what we do in this type of inversion, we have this triangle ABC. And we have the inner circle of this triangle. It intersects the triangle at DEF. Then also let I be the in center. Then we invert the figure about the in circle. Okay. Yeah. And yeah, that's it. Also, I'll just draw the circumcircle because we'll need it. Okay. So now, where does the things go? So in this figure, we have which points? We have A, B, C, D, E, F. Since it's the in circle, D, E, F goes to themselves because they lie on the in circle. How do we think about this point A? Consider this circle AEF. Since angle IFA is 90 and angle IEF is also 90, these are tangents, so these are 90. AEIF are cyclic, a concyclic. And the image of the circle AEIF is just the line EF. Do you see how? Because the circle passes through the center of inversion, so it should be a line. And we know 2 points on lying on this line, E and F, so we can construct the line. Which means A should go to IA intersection EF. A goes to this point. It's easy to see that if let's say A dash, then A dash is midpoint of EF. Why? Because notice that these two things are equal, because A and AF are tangents to encircle. This is just in radius. So we get that AI is perpendicular bisector of EF. So A dash is the midpoint. Right? Similarly, B dash also comes to the midpoint of FD and C dash comes to the midpoint of ED. And the circumcircle ABC goes to this circle A dash, B dash, C dash. So, what is this circle? This is the circle passing through the midpoints of the three sides. So, A dash, B dash, C dash is 9-point circle of triangle DEF. Right? There are many other nice properties also. One nice property is, if we consider the second intersection of this circle with the circumcircle, let's call this K. What will be the inverse of K? I'd recommend you to pause the video and think about it, what it would be. Since K lies on AEF, this implies K dash will lie on EF, because the image of AEF is FE, the line FE. And since K lies on ABC, the circumcircle ABC, this means K should also lie on NPC of DEF. It means it's a point lying on the 9-point circle of DEF and lying on EF. So this is basically this point, K dash. And since midpoints and the feet of altitude lie on the NPC, we already have the midpoint, so this should be the feet of altitude. This is nice, right? Actually, I, K dash and K should be collinear. They are not collinear in the figure. Ignore that. It's a freehand diagram, not an accurate diagram. So I hope you see how this is nice. I couldn't really gather much question on this. Like I have seen them in the past, but I could not find them now for some reason. But yeah, if you see encircle, you should be sure that you try to invert about the encircle in mind at least. That's what I do. Sometimes encircle is nice. Okay, the last configuration is, oh sorry, the last type of inversion is orthocenter inversion. Okay, how to think about this? What's orthocenter inversion? It's basically a different kind of inversion, you know. Let's see. First of all, how to motivate this inversion? This is motivated by the fact that HA into HD equal to HE into HB equal to HF into HC. This thing comes from power of point. If you don't know power of point, you can also do it by similarity. It's a good exercise. So I'd recommend the readers who don't know, not readers, sorry, viewers to who don't know to prove this on your own ones. I'll right now assume this is true. Okay. So if this is true, if I consider some inversion which sends A to D, it looks intuitive that that should all about the center H. It also looks intuitive that it should send E to B and F to C. How do we do that? Okay. So some people say negative inversion. I'll explain it how. We consider the inversion with radius root minus of HA into HD. What it means is if A is a point lying on say like this side of H, after inversion, it will go on the opposite side. Another way to think about this is consider the inversion with center H, radius root HA into HB, followed by reflection over H. What it does is it will send a point, it will send A to a point, let's call that A dash, then HA dash into HA should be equal to HA into HD, which means HA dash equal to HD. These two things are equal. Now, when I reflect A dash over H, clearly it will go to D. So this whole thing sends A to D and vice versa. Now, if I consider this whole thing, where will E go? Let's say the inverse of A is some E dash point here. HE into HE dash should be equal to HA into HD. This is the radius squared. We know HA into HD is HA into HB. So I get that HA dash equal to HB. So this thing is equal to this thing. After reflection, E dash goes to B. So in total, E and B go to each other, right? Okay. Okay, so what are some nice things about this inversion? this circle BFEC goes to itself. Why? Under this inversion, because F goes to C, E goes to B. This circle should go to a circle. We know 4 points lying on the circle. We can construct the circle. The 3 points are EBC. In fact, we know 4 points, FEBC. So this will be the same circle, right? This is a nice thing. What about, let's say, this circle? It passes through H, so it should go to a line. Notice that B goes to E, F goes to C, and D goes to A. So this circle goes to the line AC, right? What about the circumcircle? Okay, I'll erase this to get space. What about circumcircle? Where will this go? A goes to D, B goes to E, C goes to F. So ABC goes to 9-point circle of triangle ABC. This is also nice. Everything under orthocenter inversion is nice. So I hope you see why this is nice. Also, there is another inversion in this configuration, which is a nice inversion. That's not called the orthocenter inversion, but it's a nice one. So I'll show you what it is. Actually, here is a question first, which you can try to do. This involves the inversion which I'll talk about right now. So you can pause the video and prove that question. Okay, so what is happening here? X is the A Humpty point. For those of you who don't know what Humpty points are, H is the orthocenter in triangle ABC, AM is the median, and this thing is just perpendicular. So perpendicular from orthocenter to the median is called the Humpty point. It has very nice properties. There's a handout also by Rohan Goel and Arindam. Oh, I forgot by Arindam or Arindam. I think it was Arindam. On Humpty points, you can see that if you guys want to. It has really nice properties. The property which here we want to prove is prove that BHXC cycle. There are many proofs of this. It also has a proof by the inversion which we just did with this under root minus H into HT centered at H. But you can try to prove using that. But the idea which I am presenting here is I'll write it below. I hope you guys have drawn the figure in your notebooks. If not, like take a minute and draw the figure. I'll take black. Consider the inversion centered at A with radius root of AH into A. Excuse me. No. So what this inversion does is it sends H to D because AH into AH dash should be AH into AD. So H dash is equal to D. Why is this inversion nice? Since FHBD is cyclic by similarity or power of one, both of them go hand in hand. AF into AB equal to AH into AD, which is equal to AE into AC, which is equal to AX into AM. The last thing follows because notice that these two are 90 degrees, so HX DM are cyclic, which means E goes to C, E goes to C, X goes to M, and vice versa, of course. H goes to D, and F goes to B. Everything goes to each other. It's very nice. Like you can see, right? Every point we have goes to some other point already existing. So now we need to prove BHX is cyclic. What does BHXC will go to? B goes to F, H goes to D, X goes to M, C goes to E. So if you prove this is cyclic, we will already prove that this is cyclic. And these 4 points are concyclic because of 9-point circle. F, D, M, and E lie on the 9-point circle. So this is also nice. Okay, irrelevant to the question which I gave, where does the circumcircle go? Notice that it should go to a circle because it's not passing through H. Oh, no, it should go to a line. Sorry, it should go to a line because it is passing through, and the circle and the center of inversion is A, right? B goes to F, C goes to E. So we know 2 points lying on that line. We can construct the line. So this goes to the line FE. Yep, this goes to the line FE. I hope this is clear. I hope all the types of inversion are clear. What we do is we pick some nice lengths existing in the circle, existing in the configuration, nice circles, nice lengths, and try to, like send existing points to another existing points, both of which are nice, and see if other things also go to other things nicely. You know what I mean by nice? Whenever I pose some question and people say, what do you mean by nice? By nice, I mean, some special properties about that point in geometry, we can say, or like that is a very heavily used point in the question given, that I classify as a nice point generally. Okay, my neck is so. So here what we did, we exploited the length AH into AD. It has so many good things with POP. AH into AD is this, and then everything goes to each other, and it's very nice. This is what the general idea in all this inversions is. Okay, so I think this lecture is bit, that what do you say, bit lengthy already. If I can cover root BC and root BC by 2, it might get very heavy. So I'll cover root BC and root BC by 2 in the next inversion class, which I'll post pretty soon. I won't delete much. Right now, I'll discuss one problem. Let me find that problem. Okay, this is a nice problem which I found, which does not involve root BC and root BC by 2 inversion. I'll reveal the source later. It actually is a source problem. So nice. The question states, in triangle ABC, P is a point such that angle APB minus angle ACB equal to angle APC minus angle AO minus angle ABC. Confirm with the nth condition. Yeah, so this is correct. Let D and E be the incenter of triangle PBA and triangle PCA respectively. Prove that BD, CE and AP meet at the same point. This has a nice idea, like this is just the feel of inversion. So I'd recommend you to try it for like 25-30 minutes minimum. And if you still can't solve it, I'd recommend that you go up to like 1 hour or so at least. And if you still can't solve it, you can see the solution. There is the solution. Okay, we do not really need D and D by the way in this question. Notice that we just need to prove BD and CE meet at the same point on AP. So these are basically just angle bisectors of angle APB, ABP and ACP meeting at the same point on AP. This is what we want to prove. So the question is equivalent to proving. I'll just remove D and D. Why to add an extra point? In triangle APB, if I apply the angle bisector theorem, I'll get AB by BP equal to, let's call this point X, AX by XP. And in triangle ACP, I'll get this thing will is equal to AC by CP. So the question is equivalent to proving AB by BP is equal to AC by CP. Okay, now we are given with this weird angle condition. Like it's just very, very weird. But if you have like an observant eye, we can notice every angle here is of the form angle AXY. And if we consider A as the center of our inversion, like center of the circle of inversion, then this angle will be of the form AY dash X dash. We'll know this. This is nice. What we do is consider an inversion centered at A with some random radius. We don't care about the radius. Good. So now B goes to some point B dash, C goes to some point C dash, P goes to some point P dash. The angle condition given to us, I'll copy it once. This will be equivalent to angle AB dash P dash minus angle AB dash C dash equal to angle AC dash P dash minus angle AC dash B dash. Now angle AB dash P dash minus angle AB dash C dash. This is equal to just this thing minus this thing. This is just angle P dash PB dash C dash. This is equal to angle P dash C dash. So what we got is These two angles are equal. So this thing and this thing is equal, right? Now we somehow need to involve this length AB and BP. And we also need to use the fact that B dash P dash is equal to P dash C dash. So we have this similarity thing, right? Triangle ABP similar to triangle AP dash B dash. Because this thing is cyclic, right? Inverses are there. Remember this thing. This is very much used. Yeah. Oh no. What's just happening? Okay. This looks more complete. So now this means AB by BP is equal to AP dash by P dash P dash. Right. This is equal to AP dash by what is P dash P dash? P dash B dash is just equal to P dash C dash. Also similarly, we have that triangle. You can see from here. Triangle A C dash B dash similar to triangle APC, which means AP dash by P dash C dash will be equal to AC by CP. This is what we wanted to prove. So what's the nicer idea here? We can invert about a random radius and things are still nice sometimes. Okay, here is the last problem. This is you can take as a small homework exercise. This a friend of me told today only, and I like this idea. ABC is a triangle. O is the circumcenter of ABC. I perform a random inversion with center A and radius R. B goes to some B dash. Oh, what's this? C goes to some C dash. And O goes to some O dash. Let this intersection be X. I need to prove AX equal to XO dash. Okay, this thing, the proof of this does not involve any of the ideas we did in the questions today, interestingly, like the proof I know at least. But we have discussed the required concept of it in the class itself. So you can post your answers in the comment and I'll respond whosoever gives the correct answer. If no one gives the correct answer by the end of like 2 days, after 2 days after the video is posted, I'll post my solution. I hope someone will post the solution though. Also, tell me from the next lecture if I should use GGB or freehand. Idea was nice. I personally like freehand, but it's up to you. If you guys are comfortable with GGB in a class, I'm fine using that. And in the next class, here is the plan for the next class. In my next class, I'll be doing inversion only. I'll first begin with root BC inversion. And then root BC by 2 inversion. Both of them I'll be discussing which point goes to what thing and how are they nice and what are these things. And I'll be doing some problems for both. I expect to do like 3 to 5 problems at least, but all of that depends on time. I might also do some hard problems, depends. Okay, thanks a lot for watching. Bye bye.